All right, so today I'll be going over Lab 2 for E533. The purpose of this lab is to get familiar with Xilinx ISE CAD tool version 10.1. I'll go through the tutorial for the assignment and then learn all the ins and outs of the program. I'll review the schematics for full adders, subtractors, bitwise and bitwise OR operators, and shifters. Um, so first I designed or implemented the 1-bit full adder schematic. So there's two XORs here, next an OR here, and then three ends. And you have inputs A, B, C, the sum, and the carry out. Um, and then after I did that, I implemented the 8-bit full adder schematic, um, which is just eight 1-bit full adders connected to each other. You have the carry in here, the the A and B inputs, the sum, and then the carry out that's connected to the carry in of the next um, 1-bit full adder. And then it just continues for 8 times. Um, because there's 8 bits in this 8-bit full adder. And then you have um, A input, B input, 7 through 0, then sum 7 through 0 bits. After that, I tested the I tested the 8-bit full adder. So here's my test bench. Basically just going through inputs and adding 1 plus 1, and then 2 plus 2, and then this um, this helps with um, trying to find or like looking at the functionality when um, the for the carryout, and then this also helps with the carryout functionality, and then this helps just test the overall functionality. So let's go ahead and simulate mutation. 8-bit full adder test bench, and then go here, and then let's do that. So here you can see it adds 0, 0, which is 0, 1, 1, 2, 2, 2, 4, and 1 to all ones, which is 0, but the carry out is 1, and the carry out is 1 here as well. So it seems to be working correctly. And then I moved on to um, extending the 8-bit full adder into a 32-bit full adder. So I'll show that here. 32-bit full adder schematic, which is just 4 8-bit full adders connected to each other. You have the A and B inputs, and then the sum, and then there's 4 of those, each containing 8 bits, which is a 32-bit full adder. And then I wrote a test bench for this to test out the 32-bit full adder, which is here. Pretty much the same format as the last test bench that I did. Um, so let's test that out. 32-bit full adder test bench processes, rerun all. All right, so you can see 0 plus 0 is 0, 1 plus 1 is 2, 2 plus 2 is 4, 1 plus all ones is 0, plus carry out is 1, and then this is just testing out the functionality. So, all right, and then um, oh, let's do this. 2-bit full adder. All right, so now we're going to um, look at the mapper log file. So I'll just map it. And then as you can see, the number of 4 input LUTs is 64. Number of occupied slices is 48. And yeah, so that's the mapper log file. All right, so let's go to the subtractor that I implemented next. So I went ahead and implemented the 1-bit subtractor, which looks like this. Pretty similar to the 1-bit full adder, except this one has 2 XORs, 2 inverters, and then 3 XORs, 2 inverters, 2 AND gates. An A and a B input, which is the same, but then B in, borrow in, and then a borrow out. Um, and then let's look at the 8-bit subtractor. Which looks like this, which is pretty much the same as the 8-bit uh, full adder, um, except there's borrow ins and borrow outs, as you can see. Borrow in, borrow out, and then they're all connected to each other. A and B inputs, and then the difference that's outputted. And then I went ahead and made a test bench for this one. Let's go ahead and test it out. Right, so you have 0 minus 0 is 0, 1 minus 1 is 0, 4 minus 2 is 2, 1 minus 2 is this with the borrow out, and then you have 80 or AA minus 5, which is 5, and then 80 minus 1, which is 7F, which checks out. All right. And then I went ahead and did the 32-bit subtractor, which is here, which is the same thing as the 32-bit full adder, again, except with borrow in, borrow out, and then 32-bit A, 32-bit B inputs, and then a 32-bit difference output. Files, and then let's go. And then I created a test bench for this. 32-bit subtractor test bench, simulate. All right, so as we can see, 0 minus 0 is 0, 1 minus 1 is 0, 4 minus 2 is 2, 1 minus 2 is all ones with borrow out as 1. Um, A minus this is this, and then 0 minus 1 is 7 FFFF. And then 0 minus this is this with a borrow out as 1, which all checks out. Um, and then let's look at the mapper log file for this. Let me go here, set it as top, generate the map report. And then we can see that there's 91 for inputlets that were used here. And then 98 is the number of bonded IOBs. Next, we can look at the bitwise AND schematic. It's basically a bunch of AND gates, each of them with comparing a bit from A and a bit from B. There's 32 of those. We have 32-bit A input, 32-bit B input, and then a 32-bit O output. And then the test bench for this is here. You can see it's 0 minus, or comparing 0 and 0, all ones and all ones, alternating bits, random binary patterns, upper half and lower half, and then the hex equivalent in binary. All right, we'll do that. Rerun all. Yes. All right, so we have 0 compared with 0, which is 0. 1, all ones, and all ones, which is all ones. Alternating bits, which is 0. And then this, and this checks out. And then we can look at the mapper log file. There's 32 out of 32 for inputlets. And then 96 is the number of bonded IOBs. We'll look at the bitwise OR next. Pretty much the same as the 32-bit and bitwise AND, except this time it's with an OR. So you have a an A bit compared with the B bit. You have 32-bit A input, 32-bit B input, and a 32-bit O output. That's the schematic. Set it as top. And then look at the test bench. It was OR. or together zeros, ones, pretty much the same set of tests as the eight or the bitwise and. So let's simulate 0 and 0, 0, 1, 1, 1, all ones and all ones, one, all ones. Alternating bits, I think, is all ones, and then this makes sense, and this also makes sense. Um, we can also look at the mapper log file for this. Map report. Use 32 for input lets, and then 96 is the number of bonded IOBs. For this one. Let's see, let's see. Um, and then I did a 32-bit left shifter, which can be shown here. Basically, you have 32 of these, which is two AND gates, uh, and an OR gate. The two ends are OR together. You have an inverter connected to the shift input signal, and then another AND input connected to the next bit input, um, and that just cascades over to the left. If the shift input here is one, so there's 32 of these, this kind of um, layout, and then you have a 32-bit A input and a 32-bit O output. Um, so this is the left shifter. Um, left shift here. Obviously we want to shift one every time, um, or shift every time. So you have these test cases and the inputs that you want to shift over by 1 bit. And then to do that, you can run the simulation. Uh, so it shifts over by 1, as you can see, for every one of these. Um, all right. And then we can look at the mapper. So we have 64 for inputlets and then 98 bonded IOBs. Finally, I um, coded this ALU in Verilog. Um, you have a 32-bit A input, 32-bit B input, a selector to select the ALU operation, and then a 32 output register, and then a 0 flag. You only assign the 0 flag when the result is 0. And then based on the what you pick for the ALU operation, you can add, subtract, do bitwise and bitwise or shift left and then set the zero flag. I also wrote a test bench for this. That basically just goes through every operation and tests it. We can simulate the behavioral model, which looks pretty good. These are all the test cases, and we can look at the mapper log file. Which looks like this. There's 267 4 input LUTs used, and then 100 IOPs. All right, so that's all I did. The number of gates in the 30 Verilog 32-bit ALU is less than the number of gates in the schematic 32-bit ALU. In the schematic ALU, I used a total of 310 LUTs throughout all of the ALU functions, consisting of the adder, subtractor, shifter, bitwise and bitwise OR. Whereas I used 267 LUTs throughout the whole ALU in Verilog. And this might be because the mapping is more efficient when done in Verilog than by hand. And or maybe just in terms of the way I drew out my schematics. In terms of impact on size, though, are the number of gates and the number of LUTs are not that far off from each other. Yeah, that's about it. Thank you.